Good afternoon, everybody. Welcome back to lecture number 6. So the quiz will cover up to lecture number 7. Okay? So last time, what did I tell you? Last time I told you let's have V of t to be, this is a phasor, so it has a magnitude and an angle 0. Can I do it using math? Can I do it e to the power j 0? Yes. Yeah, but remember, this is very important information. When you do e to the power something in MATLAB, this has to be in radians, okay? R means radian. So remember this quote, degrees for presentation. Radians for what? For coding. So if you do in MATLAB x j 30, that's wrong. It has to be x j pi over 6. That is correct. Even in MATLAB, if you use the function sine 30 degrees, that is wrong. You have to use sine pi over 6 or use sine degrees 60. D is for degrees. So remember this quote. Degrees for what? Radians for? املأ الفراغ. Might come in the exam, okay? Okay? So when you do the project, never ever use degrees, always use radians. So when you do the calculations, it has to be in radians. But if you use the calculator, you can use both. We can use both. Question? Okay. Let's continue. Okay, so this is a side talk. What is E of f? Can I say it's E of f? This is the absolute value. There should be an absolute value. E to the power j delta. And what is the current? IA, I told you, it's EF minus V terminal over Z. Of what? Z of S. If I do I conjugate, it is E of f, e to the power j minus delta. This minus is because of the conjugate. Minus v of t, e to the power j0 is 1, over z of s, e to the power j minus delta. No, not delta, minus theta s. Now, let's go to the expression S equal Vt Ia conjugate. It is Vt e to the power j0 is gone times E of f absolute value e to the power j minus delta minus Vt absolute value over Z of S e to the power j minus theta of s. If you multiply them, you should get theta of s because it has a minus. لما تطلعها في البسط تصير positive minus j delta. Correct? So we can do it that way. It's v of t absolute value e of f divided by absolute value, which is the magnitude, e to the power j delta minus theta of s, which is this expression. Minus, clearly the other one is Vt squared, because you have Vt times Vt, over Z of s, e to the power j theta of s. That's wrong. Theta of s minus delta. Clear? How do we move from this expression to these two? P is the real part of this, Q is the imaginary part of that. We use what we call Euler identity, okay? If we use Euler identity, what will happen? This e to the power j should be v of t e of f over z of s cosine of theta of s minus delta plus j sine of theta of s minus delta minus vt square over z to z of s cosine of theta of s plus j sine of theta of s. What is the real part? The real part is term 1 and term 3. This is term 1, this is term 3. What is the imaginary part? Sine. Oh, we have to have.
You have to close the book.
This is term number 4. And also here we have, we have to close the bracket. If you close the bracket, it will be easy. Math, this is math, okay? If you multiply this by the sine and this by the sine, you should get these two terms for the reactive power. Is it clear how we derive it?
Yes.
For all the power systems, this is what they do. They use Euler identity and then they derive it. Now, what do we see? We see that to control the real power, I either change the excitation voltage, EF, Vt has to be kept at rated. Z of S, you can change it by adding extra copper, adding more windings, adding more impedance. If you change it, you will change theta of S and the torque angle. So you have two methods of control. Change the excitation voltage, which basically tells you changing EF and delta, or change the impedance of the generator. And to change the impedance of the generator, we will talk about it today. You don't change the windings. It's just the generator, instead of connecting it with one line, you connect it with 2 or 3 lines. This way you reduce Z, effective Z. I will talk about it later, okay? But as you can see, these two equations are very important. It tells you that to control the real power and the imaginary power, there is more than one control elements. If armature resistance is neglected, what is armature resistance? Ra. If we neglect it and we just stick with X of S, we replace Z of S by just X of S, and this is single phase power. We use the 3-phase power. We will reach to the 360 equation. These are the EE 360 equations. The real power is a 3VTEF over X of S sine delta, and the Q, it was a 3V of T E of F over X of S minus cosine delta minus 3VT square over X of S. Do you remember these two equations from EE 360?
Yes.
It's very important. Now, all of you have access to EE 360 slides?
Yes.
So have a look at it and you will remember these two equations. Not only that, we can also from the power, the 3-phase power equation, we can find the torque equation. Torque is nothing but power over synchronous speed. What is synchronous speed? 2 pi 60. Because the machine has to spin at 2 pi 60. It is this term divided by omega. Omega is just a number. That's why when you plot delta over power, this power, the electrical power, 3 VTEF over X of S sine delta, you can sweep it over various deltas, starting from 0 all the way to pi, where the peak is at what? Pi over 2. You remember this from EE360. Now, if you use other angles, you should get a negative curve, but that's not a generator. As a matter of fact, you are only allowed to operate in the stable region, which is 0 to 90 degrees. The moment you exceed 90 degrees, you go to the loss of slip. You lose the loss of synchronism. You lose your synchronism. And if you think about it, the stability region has to be somewhere here, not 90. 90 is on the verge of stability. However, the maximum power can be achieved where? At 90 degrees. Should you operate your generator at maximum power all the time? No. These are one of the rare conditions, as maybe if there is a huge demand, maybe we can operate at 85, 80, but we have to be very careful. It's not only that, there are different names for this region at 90 degrees. They call it maximum power, that's the WIL 360 name, the well-known, or maximum torque, because if you draw the torque curve, the maximum occurs at the maximum power. It makes sense. They also call it the pull-out. You're pulling out the maximum power. These names are important, okay? Or the pull-out torque. The fifth name is, we call it steady-state stability limit. This is the steady-state stability limit. This is the limit where if you exceed it, you go to the unstable region. And remember, delta is the angle between the excitation voltage and the terminal voltage. The excitation voltage, you can control it by exciting the rotor or moving the rotor faster. Any change in the rotor would change it. And I told you before, it has to do with the alignment of magnetic flux of the rotor with the magnetic flux at the stator. If they are 90 degrees or more, the coupling between the magnetic flux is not stable. They would lose synchronism, and maybe that particular south pole would lose the coupling with that north pole, and it will try to find another pole that is closer in terms of electrical degrees. Okay? In the EE360 slides, there is a video how synchronous generator works. It has these rotating magnetic field. Watch it to understand somehow what I mean by angle of the peak of the magnetic flux in the stator, angle of the peak of the magnetic flux of the rotor. The rotor magnetic flux is constant, uniform, but because it's rotating, it becomes uniform rotating RMF. The magnetic flux in the stator, it's by nature AC, so it's by nature rotating. So if you rotate a constant magnetic field in an already rotating magnetic field, you have to make sure that delta alignment is there, and delta clearly impacts how much power. If you think about it, yes?
دلتا هي الفرق بين ايش بالضبط؟ شو في سؤال بعد؟
Delta is first of all, delta هي the phase difference between ال EF وال VT. ال EF جاي من الروتر. ال VT جاي from inducing voltage on the stator. If you move the rotor faster, the frequency will change, the magnitudes will change. But if you even change the excitation voltage of the rotor, you should change, also you can change the magnitude and the angle of EF. But it's not only that. Where you synchronize your magnetic flux, يعني the moment you decide you're spinning your rotor, the moment you release it, you have to make sure it is aligned. The magnetic flux are aligned to get the maximum power. If the magnetic flux lines are not aligned, they were rotating, but they will be dragging each other. يعني your goal is to make north with south aligned to each other. But for some reason, if you make it aligned to each other, this is difficult to synchronize. They would drift away if you change the road, etc.
طيب يمدينا assuming احنا بالستيبل ريجن يمدينا نغير الامبيدنس عشان نزيد
Yes, you can change it, but you change the impedance by adding external impedance, and the only way to add external impedance is to change the lines, and we'll talk about it.
الدكتور قلت انه اذا كانوا فوق الدفن نخليهم فوق بعض بالضبط.
مش الماجنتيك، هم ماجنتيك فلكس، هم عباره عن سيركلز. هنا نورث هنا ساوث، هم عباره عن سيركل.
طيب كذا اذا كانوا فوق بعض دايركتلي ما بيكون الباور انجل زيرو. الباور انجل هي كذا صح؟
Yeah, but already لا هو it's not, it has nothing to do with يعني هذا south وهذا north.
Okay.
You have to make sure that they are aligned with each other. If you add a little bit of delta, يعني it's not only by the alignment. It has to do with the alignment. It's not the only factor. Excitation is only a factor. It's also another factor. It's not only that. Yeah, what you're saying is, okay, delta zero, then the power is zero. Then this would occur if you don't have any load. You align them directly. But naturally, if you add a load, they will drift away, naturally. Naturally, they would drift away. يعني always you would find the south. هي الفكرة من السynchronous, انت you're pulling the magnetic flux toward each other. If you add more load,
They will slip.
they will slip, they will follow each other. But they will be in a uniform way. You cannot control them. يعني once they let them synchronize, naturally they will follow each other. But yeah, it's true. If they are aligned directly, delta is zero, means power is zero. But if there is a load, there is a current drawn. Because you draw a current, there will be a voltage drop on Z of S. Because there is a voltage drop in Z of S, then naturally there will be a delta.
باور زيرو قصدك الباور ترانسفير تو
لا لا. This is Z of S. This is V of T, صح? This is E of F. صح? If you add a load, there is no load, Vt equal EF, delta is zero. The poles are aligned. The moment you add the load, في current بيمشي. This current would change the delta. The only way for the current to flow is if delta is changing. And EF, the excitation would change because of the excitation. If you add Vt has to be fixed. 13.8 kilovolt, cannot change. There is a control mechanism to fix it. The only thing that changes is E of F, which is either the excitation or the delta, the magnitude or the delta. If they are aligned, delta is zero. Let's talk more about it. So power system stability is the property of the system that ensures it will remain in synchronism and maintain the state of equilibrium following disturbance force. There are two types of disturbances that occur for a generator. There is a gradual one and there is a sudden one. The gradual one is the steady state stability. It means we are operating at a constant power. For some reason there is one house that wanted more power. So gradually we increase the power. There is gradual increase in the load. Everything would change smoothly. There is no ripples. Why we use Simulink is to capture those changes. Are they safe or not? For some reason, if all the houses in the neighborhood decided to shut down power, that's a problem for electricity. Because this is what we call it sudden changes in the load. It's not gradual. It's sudden. All the neighborhood decided to turn off electricity, there is a sudden change. This is what we call it transient stability. And this has to do with severe disturbances, outages, faults, short circuits in the distribution lines or in the transmission lines. Sudden changes is transient. Which one is more dangerous? Transient. So steady state stability is the normal day-to-day operation. And it becomes predictable. You know that this house would turn off the power at 12 midnight. So we expect low power at night. So they go to the control of the generator. They reduce generation naturally. But if for some reason you're generating normally and there is a huge demand, what will happen? Blackout. Because you cannot supply enough power. The transient is too much that there is a severe disturbance. It turned out that this has to do with not only the generator, it's only the transformer and the transmission line. But hold on a second. I already told you that the power has to do with X of S at the denominator. But this is just the power that's leaving the generator. But you as a power engineer, you care about the power that's leaving the generator, going through the transformer, going through the transmission line to the infinite bus. The term infinite bus is the pool of the grid. It means if you give it, it doesn't care. If you leave out of it, it doesn't care. It will maintain a constant voltage, E of S at delta of S. This is what we call it single machine infinite bus. You connect a single machine to an infinite bus. Infinite bus, it means if you lose power here, there is enough generators in the system that will suddenly compensate the loss of power to maintain the voltage. Suddenly compensate the absence of this generator power. It will inject more power in the grid. Once it injects more power in the grid, even if this is discontinued, the voltage here would remain constant. That's the definition of infinite bus. It's the system is large enough that it won't be bothered by a loss of one generator. Clear? So, for a single machine infinite bus, the power transfer, I'm talking about here power transfer, how to derive this equation? Same concept. S is V of this generator times V of that generator. You subtract the voltage, divide by the impedance, you multiply by all of them, then you reach out to this term. It turns out that this is also relevant to delta, because in the infinite bus, delta of S is 0. It's taking as the reference. It's the infinite bus. It's the slack bus. Infinite bus is a slack bus. It is the reference. So it turned out delta, which is delta G minus delta S, if you have delta G not to be 0, delta of S 0, the difference is delta, so delta G would equal to delta, then the delta of S is 0. Then you would notice that you are impacted by X of the generator, and X of the transformer, and X of the line. So now power engineers, do they have to change X of the generator to control the power if they don't want to change the delta?
No.
They can change X of transformer, they can change X of the line. Which one is easier? It's the lines. Let me give you an example. If you have a line of impedance, J5, can I make this impedance 2.5? Yeah.
Yes.
Just add a parallel line. J5 parallel J5, that's the equivalent. J2.5. And easily you can have it by having a breaker. You usually have breakers. If you have these two breakers now closed, you have equivalent impedance of 2.5. So you can control it by controlling which lines are connected to my generator. So you as a generator, the more lines are closing their breakers to you, you should estimate the impedance, and based on that you calculate your power. In 463, you were told that the generator it has this fixed voltage, fixed current. But as a matter of fact, even what you do in the grid impacts the generator. And it makes sense. Generators are not isolated. They're part of the grid system. They're part of the grid. Clear? If you draw the equivalent circuit, it's two generators. This is the infinite bus. This is the synchronous. And you sum all of the reactances. We ignore armature resistance. We ignore armature resistance. It turned out there is something with synchronous generator that's really important, this power angle characteristics. Let's look at point A. This point A, this is electrical power. That line is the mechanical power. This is what the diesel prime mover is told to generate. Constant. So the synchronous generator is driven by, let's say, an internal combustion engine, diesel, fuel, gas. It has a constant power, which crosses the electrical power, the electrical generator power, through points A and C. If I'm producing less electrical power below what I'm providing in the prime mover, my prime mover would swing more into pushing more mechanical power such that I reach equilibrium. If I reach equilibrium, I would stay at point A. If for some reason I'm having more electrical power, the prime mover would slow down. It will put me back at the equilibrium point A, which is the constant power that I want. I want my generator to operate at constant real power. It turned out there is a dynamic equation, which we call it the swing equation, where the difference between the electrical torque and the mechanical torque in the shaft, in the coupling, so the synchronous generator, which is the electric motor, the machine, there is the prime mover, which is a mechanical engine, there is a shaft that's connected, there's a coupling between them. If there is more torque in the electrical engine, I'm pulling my mechanical engine to rotate more, they're coupled. This has to do with the inertia as well as the acceleration. This is mechanical engineering. Inertia times acceleration. Inertia has to do with the inertia of the whole two system, the whole shaft, the whole rotor in the generator, and the shaft side of the mechanical engine. If the torque between them is zero, no need to accelerate. If the torque is positive, my acceleration, if the mechanical shaft is more, torque is more than the electrical torque, I need to accelerate my electric motor. This J has to do with the electric motor, the acceleration of the electric generator, that most electric machine. If I'm having more torque in the electric machine, I'm coupling it with the mechanical engine, which is fixed by command. I know how much diesel I burn, it's fixed. The electric motor or the electric generator would have a negative acceleration, so it would decelerate back to the equilibrium point. So let's have some examples. So if I'm operating, if my electrical power is more, it means my mechanical torque is larger than my electrical torque. My mechanical torque is smaller than electrical. If P electrical larger than P mechanical, it implies torque of electrical larger than torque mechanical, صح? It means this number is what? Negative. It means my acceleration is negative. So I need to go back to this point. If my mechanical power is larger than electrical, so my mechanical torque is larger than electrical, it means this is positive. It means acceleration is positive. It means I have to go back here. So this is the definition of stability. If you go to the unstable region, let's say the electrical power is here. So P electrical is larger than P mechanical. So torque electrical is larger than torque mechanical. So the d omega dt is less than 0. It means I'm going this way. I'm going to the 90 degree. So this is unstable. You see it? If my mechanical input is larger than electrical, meaning here, my mechanical torque is larger than electrical, my acceleration is positive, it means I'm drifting way here. So that's why we call it unstable region. So the fact we call it stable is unstable is because I have a mechanical input power that is governing my dynamics through the swing equation. Is it clear? And I will share with you a file that explains the dynamics, but I think this is clear.
يمكن هذا الكيرف لأي ماشين في العالم ولا
No.
specific machine معينة؟
No, this is a synchronous generator curve for every synchronous generator. The constant line is the prime mover, mechanical power that is fixed, constant.
أيوه.
If you push more gas, this will go up. If you have a little gas, this will go down. Who controls this? There is control mechanism that link these two together in the stable region. That's why you cannot operate in the unstable region, because the control mechanism that is governed by the swing equation would decelerate, would accelerate toward not the stable point.
This is only for the synchronous generator, not the motor.
No, synchronous generator. For synchronous motor, it's a smaller application. Big application is synchronous generator. Synchronous motor is synchronous motor. You provide electricity to get this PM. So this is your output. So you control your machine to get that line. It has similar dynamics, but that line is not controlling the machine. For a generator, that line is controlling the machine.
طب دكتور نقدر نقول انه لما الميكانيكال تكون الميكانيكال تورك اقل من الالكتريكال تورك تودي اكسلريت لانه الالكتريكال لازم يسحب معه الميكانيكال
Because of the coupling between الشافت حقت الالكتريك ماشين والشافت حقت البرايم موفر. هما they are coupled، يعني زي ونش السيارة مربوطين في بعض. بس the problem انت عندك you can control the mechanical input either through closed loop or whatever happens in the electric motor. انت عندك two machines, they are impacting each other. How do they impact each other? By the inertia times acceleration. Torque, the delta torque equals inertia times acceleration. If you have bigger synchronous generator, the acceleration would be less. And if you have the prime mover, inertia is much smaller than the generator, you do not need to accelerate or decelerate. It will be very slow. If you have a very small synchronous generator, the acceleration or deceleration will be larger with the changes with the mechanical input. But that's not the problem. The problem is that you have load or a grid that has electric current that controls the magnetic field of that machine, that directly controls their coupling between. Is it clear? So now you understand in this course, maybe it's better to do homework on synchronous generator, explore it. I'm not going to ask you to build it from scratch. What I'm going to ask you is I'm going to ask you to go to File, go open see examples of synchronous generator, and run them, and tell me what you see. Maybe adjust the power. Never ever in any simulation software start from scratch. They put the examples for a reason, to save you time. So when you do homework 1, I haven't developed it yet, but I will open my computer, I will go to File, I will go to Open, I will see that the example they provide. I will ask you to change the parameters to another system and run the simulation. This is what I'm looking for. This is the skill set that I want you to master. Do not put everything from scratch. Never. Okay? For a simple answer is if you work for the company, your time is more valuable. Would you rather finish the homework in 1 hour or finish it in 6 hours? So help me, okay? So I'm telling you what's one of the questions now gonna be in the homework, okay? By developing this skill, when it comes to the project will be way more easy, and we can have better outcome. That's what I told you. What are the methods to improve the stability? 2 methods. Increase the excitation of the generator, reduce the reactance of the grid, the network. So in the excitation, so this is the hydraulic turbine and governor. This is the excitation system. If I increase the excitation system, I increase EF. Remember, V terminal is fixed. This is R means receiving end. This is sending end. This is receiving end. I usually want to have these voltages to be constant so that it doesn't ruin the grid dynamics. So if you change EF, you can change the power, but you have limited access to EF because how do you change an EF? You either spin it faster, but you change the frequency, or you increase the small EC input. You remember it? Or you increase the magnet in the pilot. You remember it? Or you change the windings, or you change the whole rotor to come up with another design. But this is limited, so they said, okay, change the impedance of the line, have them as 2.5. If you have them as 2.5, your total X will be less. If your total X is less, if you reduce the X, your power will be more. So question in the exam, a synchronous generator would more likely produce power if it has multiple lines connected in parallel or one line connected, given that the lines all have the same impedance? Multiple lines. That's why in high transmission lines, there is always two parallel lines, three parallel lines. You remember those cables? They have two, 3 phase here, 3 phase here, and one tower. So that they don't build a tower for every line. But there is a problem. The more lines you have, the more money you put. So the cost is the constraint. The cost of having more lines is an issue. We would love to have infinite number of transmission lines. Our life will be much easier. But what's the problem?
Money goes.
You have to put money. You have to buy lands. Any land under any transmission line, nobody is allowed to use it for building or farming or streets, except very few highways that go under transmission line. But this area is useless. You're wasting it. Okay? So in the next lecture, we will continue the discussion about the field change. But what I want you to know is that stability is very important for synchronous generator. Okay? Any other question? So, the homework